In this discussion, we're going to talk about using calculus to determine or calculate the amount of work done by some action. And you can see I've written here that work is equal to force times distance. Now, first, it's a little oversimplification, and I'm going to start out with oversimplification as we move through more and more difficult situations. This should really say that work is equal to the force applied in the direction of the displacement. The direction of the displacement times the distance of the displacement. Sometimes the force is actually applied maybe at an angle, but the important part is, excuse me here, can't talk and write at the same time apparently. In some cases, force is applied at a angle, if you will. Okay, maybe we have something and the force is applied in this direction, but the only force that matters, this is the component of that force that's moving this object, maybe say along the ground here, and so that object ends up being over at this position. And so it's this force that we would be talking about rather than the actual force applied. It's the force that's in the direction of the displacement, and then time, and the work is that force times the distance that that object moves. Well, what I want to do is take us through a progression of different things, because what we're going to, well, let me just write up a little problem or a little notation here, and we'll continue. Okay, so this question, as you can see, is determine the work done by lifting a 150-pound object 10 feet. Lifting 10 feet, and we're assuming directly up. So this object at the end of our job would be up here. Okay. So there our object is after we've done the work. Now remember, work, I'm going to illustrate with a W, is equal to force times distance. Now, in general, force can be thought of as a push or a pull. Push, pull, I guess, or a lift, as we have here. And again, we're going to refer to, in this case, the simplest cases, to displace something that weighs 150 pounds. That is, to overcome the force of gravity. And gravity is what makes that weigh 150 pounds. So to overcome the force of gravity, we have to apply a force in the opposite direction and equal to that gravity, or more. If we apply exactly the force to overcome the gravity, then it would be a 150-pound force. So in this case, we have work is equal to, and the force that's being applied is 150 pounds of force. Okay, 150 pounds of force. And the distance this is traveling is going to be 10 feet. And so the work done by lifting this 150-pound object is 10 times 150, or 1,500, pardon me. And we say, in this case, the label, the work units are in foot-pounds. Okay, that's what we call it. So, in fact, there are different units of work. We're going to stick primarily with foot-pounds. But you can see that there are different labels of work. And let me list some of those different labels below, some of those different units of work below. You see, I've written some units of work. What we're going to stick with primarily is foot-pounds, but it can be also labeled in inch-pounds or foot-tons. These are the common, this is using the U.S. measurement system, which is probably currently most common in engineering practices. When you go to scientific or physics particularly, then you'll see work labeled in ergs or joules, and that's a more or less a metric system where a dyne, say an erg is dynes per centimeter, a dyne is a measurement of force. You see joules is Newton meters, and Newton is a measurement of force, and they're a little less clear. In physics, of course, you'll study those, and it's a little less clear what those actually mean. And by the way, one dyne is the force required to produce an acceleration of 1 centimeter per second on a mass of 1 gram. And by the way, a newton is the same. Okay, a newton is a force. It's the force required, and I'm out of room here, force required to make 1 kilogram, okay, accelerate at the rate of 1 meter per second, or per second squared. So the Newton is also a measure of force, as I was saying before. Now, all this aside, we're going to stick with dealing with foot-pounds. So I want to go now and kind of extend this idea of what we did here into something that's going to be useful for us as we proceed through lifting things that are not solid, like trying to pump a liquid out of a tank. Okay, we're going to look at this same object, but I've put a little more information in here, and we're going to do what's called incrementalize the height of the object, and that means we're going to think about lifting little tiny slices one at a time and finding out what work is required to lift a little tiny slice, and we're going to add all those up using integration to find out what it takes to lift all of the infinitely tiny little slices. But I've put some dimensions on this so that we can talk about it. So this is our same 150 pounds. The object still is 150 pounds, okay? And we're still going to lift it, okay? We're still going to lift 10 feet. Now, for the sake of argument here, notice that the dimensions, the volume of this box, let's see, the depth is 2 feet, the width is 15 feet, and the height is 5 feet, as I've indicated here. And so the volume is 150 cubic feet, 150 cubic feet. So what that means is the density, and we'll assume this, that the density is 1 pound per cubic foot. That is, 1 cubic foot of this weighs 1 pound. That's our density. Okay? Or we could say density is equal to 1 pound per cubic foot. 1 pound per cubic foot. That's the density. And since we have 150 cubic feet, then this thing weighs 150 pounds. Okay. Now, in fact, let's write this down. Here's what I'm going to do. In general, volume V is equal to, and I'm going to put these in capital letters, length times width times height. Okay, length times width times height. Now here's what I'm going to do. I'm going to imagine taking a slice out of this little piece. A little tiny slice. Okay. Now, this slice is actually infinitely thin. We've kind of seen this idea before, haven't we? So it's back there someplace. I can't get it all the way through. So we've got this little tiny slice. Now, for the volume of this slice, okay, so let's look here. The volume of the slice. And let me write it this way. The length, if you will, the width of this slice is still 15 feet, okay? And the depth of this slice, let's see, looks like it's 2 feet. The height of the slice is infinitely small. So that measurement right there, that tiny little height, that's infinitely small. And it's vertical, so I'm going to call it dy. We've seen this idea before. Okay, so there we have the volume of that slice. Now, so let me write it in this way. Let me come up here. The volume of that slice is equal to what? 15 times 2 or 30 dy. Now remember, the weight is equal to the force, or the force is equal to the weight. Maybe I really should have said that. And in this, required to move this. And in this case, that weight is 75 dy pounds, okay? Because that's the volume that we just found of that slice. 75 dy pounds, that's the weight, or the force required to move, okay? So remember now how we calculate work, but let's talk specifically about calculating the work to lift that infinitely small slice 10 feet. Well, it would be the force, remember, times the distance. And in this case, the force is 75 dy. And the distance is 10 feet. So we could say the work required to lift that. Now, we're not lifting the slice to the 10-foot level. You know, when we lift the whole object, all parts of that object are being lifted 10 feet. The bottom of that object will be at the 10 feet level, but the slice will be above that. The slice is going to move 10 feet. Okay, anyway, so the work required to move the slice 10 feet is 70. I said 750, and I'm sorry, it's 30. Where have I gone wrong? I apologize to you. This is 30 dy. This is 30 dy. This is 30. My bad. I apologize. 30 times 10, or 300 dy. Okay, now, to calculate the work in total, the total work, okay, and here's the idea. We've got this box, or this object, cut into these horizontal slices that are infinitely small, and to lift one of those infinitely small horizontal slices is this 300 dy right here. So what we're going to do is we're going to add together what it would take to lift all of the infinitely small slices, okay, and the work required to lift one. In fact, one particular slice is 300 dy. I probably should have written that as the integral to lift, the work required to lift one slice, okay, is this 300 dy. And where do those slices start? Well, they start at the bottom of the object, which would be 0 feet. They'd start way down at the bottom down here. But where do the slices go? Well, they only go up to 5 feet. See, we're adding the work for each of the slices between 0 and 5 feet of the object. And we already found the work in here to lift a slice 10 feet. So we're adding up, if you will, the work required to lift all of the infinite number of slices with this integral. So that's just basically the integral from 0 to 5 of 300 dy. Well, the integral of 300 with respect to y is 300y. And we're going to evaluate that with this definite integral from 0 to 5. And so, of course, that's going to be 300 times 5 minus 300 times 0. and you see that we get 1,500 minus 0, or 1,500 foot-pounds. Just as we did before when we didn't think about this incrementalization here, okay? On the next page, I want to talk about how we could calculate the work if we incrementalized in the width of the object rather than the height of the object. Let's go to the next page. I've redrawn the box along with its dimensions. And as I said, we're going to calculate work by incrementalizing the width of the object rather than the height of the object that I did last time, which means we're going to take slices that are vertical instead of horizontal. So I'm taking a slice like this through this box. And when I do, of course, what's it going to give me? Something like this inside, isn't it? Okay. But I've got this infinitely small slice in here. Okay, now, what I want to do is calculate the work required to lift that one slice 10 feet. Okay, and so we have to calculate the weight of that particular slice so that we'll know the force. And to calculate the weight, we need the volume of that slice. So in this case, volume again is length times width times height. And you can see in this situation, we have this little narrow piece, okay, this narrow dimension, that is measured horizontally, and that's like we measure x's. And so I'm going to call that dimension dx. And of course, we've got a dimension of 5 feet and a dimension of 2 feet. And so in this case, the volume of that slice is the 5 feet by the 2 feet by the dx feet, okay? And of course, that's 10 dx. That's the volume. And the force then for this particular slice, that's the volume of a slice, I should have said that. And the force required to lift this slice 10 feet would be the weight of this slice, okay? The weight of the slice, that's good, the weight of the slice, excuse me. And the weight of the slice, since 1 cubic foot weighs 1 pound, is just the volume, okay? In this case, it's going to be the volume of the slice, that is, times 1 pound per cubic foot. So just one, that it will be equivalent to that volume. Okay. So in this case, that force, let's calculate that force. Well, that force, just as I said, is the same as the volume, which is 10 dx. Okay, so the work required, W for work, required to lift that slice 10 feet is going to be the force required to lift the slice required to lift the slice at all times the 10 feet. And so in this case, that ends up being what? 10 dx, that's the force, times 10, which is 100 dx. So as before, then, what we're going to do and I'm sorry here, I feel like I haven't made something clear, so let me back up for just a second. Remember, in a lifting problem, okay, and that's what we're talking about here, in a lifting problem, the way we're dealing with this is force is equal to weight. And so above, let me recall what we did. Weight is equal to volume times density. So above, what we ended up doing is I called the force of the slice, which was that was equivalent to the weight of that slice. Whoops. Of the slice, my bad. Okay. Is the volume of the slice times the density of the material. And the density of the material is 1 pound per cubic feet. Now, the volume of the slice was, 10 dx? But now this is a volume, so it was 10 dx cubic feet. And we're multiplying that with 1 pound per cubic feet. And so that ends up being, the cubic feet cancel, and so we have 10 dx pounds of force. That's the weight of the slice, and so it's the amount of force required to lift. Okay, I apologize, I backtracked there. Okay, so here's what we're going to do then. We know the work for one particular slice is 100 dx, and I marked up here. Remember, it was the force times 10, and so 10 dx times 10. So we know the work required to lift one slice, so the work in total, this is the total work for the entire object, okay? Total work for the entire object. But what we're going to do is we're going to add up all of the works, all of the amount of work that it requires to lift each of the infinite number of pieces added together, work for all of them. So that's an integration. So we're going to integrate each of these works, okay? So we're adding up the work of all of the possible works that are involved. Well, what are we going to do? We're going to start these slices over here at the left edge of this box or object, and we're going to move those slices all the way across to the right edge. Well, we'll assume the left edge we're thinking of at the 0 level, and the right edge, since this object is 15 feet wide, we will integrate to 15, 0 to 15. And of course, then we get what? Integrating 100 with respect to x is 100x, and we're evaluating that from 0 to 15. And when we do that evaluation, that's 100 times 15 minus 100 times 0, which is, of course, just 1,500 again. And these are foot-pounds, okay? Foot-pounds. So it didn't matter whether we incrementalized horizontally or vertically, okay? We got the same result. Next page, we're going to incrementalize one more time before we get on to some actual problems. These are giving us an idea how we're going to set things up in the future. Okay, as I mentioned, and as you see here, I've drawn another diagram. We're going to incrementalize the distance moved. Now, in total, we're lifting that entire object 10 feet. But what we want to do is say, what's the work required to lift it an infinitely small distance? Okay, so what's it required to lift it that distance? Now, we'll call that's infinitely small. So we'll recall how that we call those things dy. I just had to make it look big enough so that we could imagine it. So we're incrementalizing the entire 0 to 10 feet. We're going to lift little pieces at a time until we're going to lift little amounts at a time of the whole object. We're going to lift it just a little tiny bit, and a little tiny bit more, and a little tiny bit more, and a little tiny bit more. And we're going to see, okay, well, as we do that, and we finally get it lifted 10 feet, then what will be the work involved? Now, let's remember once again, the force here, and I don't need dimensions on the object this time. The object is 150 pounds, and so the force required to lift is 150 pounds. Now, we're lifting this time a distance, a little piece at a time, lifting dy. And so the work based on lifting a distance of dy is force times distance. Force times distance, and that's 150 dy. Okay? Now, the total work then to lift the object all 10 feet instead of an infinitely small amount, the total work, W, would be the integral of 150 dy. This time we're going from 0 to 10 feet. See, these we're lifting from 0 to 10 feet because we're starting these dy's way down here and we're moving through clear up to here. So that's the 0 to 10 in this case. Well, as you see, what we're going to end up with is an integral. The integral 150 with respect to y is 150y, and we're going to evaluate that from 0 to 10. And you can see once more, it's not difficult to determine that we get 1,500 one more time, and these are foot-pounds. So it didn't matter how we incrementalized things, we got the same result each time. Now, the reason this is important, you'll see in the next problem. And this is a real type problem as opposed to what we've been doing here in preparation for what we're going to do in these next few problems. As you can see here, we have our first problem involving actually calculating work. We have a 16-foot tall cylindrical tank that has a radius of 8 feet and is half full of oil, and the oil weighs 50 pounds per cubic foot. Find the work required to pump the oil out through a hole in the top of the tank. Well, I've drawn some kind of diagram here to illustrate, and you can see in the middle, of course, in total, we look at the top of the tank and the bottom of the tank, roughly here. We need to some way discuss how we're going to refer to that. And so I'm thinking in terms of the y-axis, so I would say that this is at the value 0, that's the bottom, and this is as high as 16. Now this level of the oil that we have in here is at the 8-foot level. And I'm thinking of measuring this, like I said, as a y value. Really is not special. I could name it by x. I'm thinking in terms of y value. And we know that the radius of this tank, if you will, is 8 feet. So along here, we have an 8-foot radius. Now, of course, that means the diameter of the tank is 16 feet, as we know. Okay. Well, here's what we're going to do. We can't, because the idea here is different than what we had with the solid object previously in the introduction. That you see here that we're not lifting all of that oil 16 feet or 8 feet or whatever. The oil that's at the very bottom would have to move 16 feet to get out of the top. The oil that's at the very top of that level of oil would have to move 8 feet. And there's some that would move 10 feet and so on and so forth. So to move all of the oil out of the tank is going to actually move different distances. So what we're going to do is incrementalize the level of the oil in the tank. That is, how we're going to think about this is we're going to take an infinitely small slice of oil, okay? So I'm just thinking in these terms. I'm taking an infinitely small slice of oil. Of course, you know, there's the back of it. Infinitely small slice of oil here. Now, because that slice of oil, that the height of that slice, if you will, is dy. And if you look at that slice of oil, that's actually a real short cylinder, isn't it? So let's talk about the volume of that cylinder, the volume of the slice. Well, how do we calculate the volume of the cylinder? It's pi times radius squared times the height. And in this case, let me rewrite this. In this case, the volume of that slice, well, of course, pi times r squared. Well, in this problem, the r value is 8. So that would be 8 squared. And the height of that slice is dy. So we could say that it is 64, let's write it this way, 64 pi dy is the volume of that one slice. Now the weight of that slice then, the weight of that slice would be the volume times the density. It'd be the volume of the slice times how much it weighs per cubic foot. And that would be 50 in this case. Okay, that's the density. And so we see that the weight of the slice is 64 pi dy times 50, which of course comes to being 3,200 pi dx pounds. 3,200 times pi, it's not dx, pardon me, dy, and that's measured in pounds. Now, back from what we were doing earlier, in general, work is force times distance. So here we have some thinking to do. Force times distance. So the work for a particular slice to move it out the top would be the force, but now remember, in this case when we're lifting, the force is the same as the weight, isn't it? So the force in this case to move a slice, and a slice weighs 3,200 pi dy. And the distance we're going to move that's the big question, okay? That's the big question here. So here's what we think of. Suppose we're at this particular measure. Remember, we're measuring y's actually from 0 to 8, but in terms of how it's a vertical distance here. So we'll assume that this particular slice is at the level y above 0. So we're measuring above 0. So that might be at the 5-foot level of that half-full tank. That's the y level. Well, how far is that being lifted then? It's being lifted from its level all the way up to 16. And that would be 16 minus y. Okay, 16 minus y, because the entire height is 16, and we're not having to go the first y amount. So that's being lifted from 16 minus y. So that's the distance. So the distance in this case, that question mark, is the 16 minus y. Okay? So the work required to move one slice, if it's at the y level, is 3,200 pi dy times 16 minus y. So let's rewrite that as 3,200 pi times 16 minus y dy. So the work in total then, the total work, see that was just to move that one infinitely small slice of the oil. So the total work, we would need to add up the work from lifting each slice that we might have. And where are these slices going to start? Well, they're going to start at the y level of 0. And they're going to go to the y level of 8 because we have no oil above the level of 8. So we're going to add up all of the different work values for each of the different slices. And of course the work for each slice we have above, so what we need to do then is integrate from 0 to 8, 3,200 pi times 16 minus y dy. Now we can do this without a great deal of difficulty, and I may not go all the way through the rest of it. The 3,200 pi we could certainly factor out, couldn't we? of 3200 pi times the integral from 0 to 8 from 0 to 8 of 16 minus y dy. But when we integrate 16 minus y, we end up with what? 16y minus 1/2 y squared. And we're evaluating that from 0 to 8. Well, as we do that calculation, we would have 3200 pi times 16 minus 8, 16 times 8, 16 times, we're replacing the y's with 8, minus 1/2 8 squared, and then we subtract from that, replacing the y's with 0. So 16 times 0 minus 1/2 times 0 squared. And of course, that's all 0. So after all the calculations come through, which I'm sure you can complete this, we get rounded to the nearest foot-pound, the nearest integer, 965,097 foot-pounds. Remember, that's our measurement, foot-pounds. Now, we might ask this question next, so along with the same problem. What would be the case if the tank was full of oil? How much work would be required to pump all of the oil out of the tank, and rather than just half tank full of oil? And obviously one guess we could make is it would take twice as much work. But I suggest to you that that is not going to be the case, because remember, when we look at the top half of the oil in the tank, if we have it half full, well, none of that oil is having to move nearly as far to get out the top. So it's not going to be double the work. Let's look at it real quickly on the next page. Okay, now we're looking at the same problem, but the tank is completely full of oil, the 16-foot tall tank that has a radius of 8 feet. Okay, so along here is our 8 feet, full of oil. And we're going to approach it the same way. We're going to look at any particular spot in the oil and look at an infinitely small slice of that oil. We'll call that level y, and y is anywhere between 0 and 16 this time, isn't it? Okay. Instead of between 0 and 8 when we were just half full. So we're going to call the height of that slice. Remember, that's a disc, if you will, or a real short right circular cylinder, and the height of that cylinder or that slice is dy. Over here, I'm sorry, I put dx. I apologize. This is a dx, a dy, a dy. Okay. And so how do we find the volume? Of course, it's pi r squared, pi times r squared times the height. And in this case, again, the radius is 8, so we get 64 pi dy. Now the weight of that slice then will be the volume times the density. Remember, the volume is in cubic feet. And so we have the volume, which is 64 pi dy cubic feet, but the oil itself weighs 50 pounds per cubic foot, so we get the weight is 64 pi dy times 50 pounds, and that's 3,200 pi dy pounds. That's the weight of that slice. Okay, well, we've seen how that was set up before, so our total work, rather than, the work for a slice would be the same. It would be the weight times the distance. I guess I ought to write that down as we did before. So the work for a slice, to lift a slice, will be the force, which is the weight, the force times the distance that it's going to be moved. Okay, times the distance. Well, the weight is the 3,200 pi dy pounds. The distance it's going to move depends on where that slice is. And we're saying that slice is at the level y. Now remember, y could be at the bottom, it could be at the top. Y is somewhere between 0 and 16. But when we move that level of the slice out the top, we're moving it 16 minus y. We're taking the entire amount, but we don't have to move it the entire amount less y. So that's that value there. So the distance, again, that is being moved is 16 minus y. So the total work that we're going to do is we're going to add up the work that's required for each slice, and we have an infinite number of those slices. But those slices this time are starting at 0 as they did before, but since the tank is full, we can have a slice that's all the way at the top, 16. So we are going to have an integral from 0 to 16 of 3,200 pi times 16 minus y dy. And when we calculate this time, we'll get, and you can go through that calculation without any problem, we'll get 1,286,796, and of course, remember this is measured in foot-pounds. So it's not nearly twice as much as if we're moving just half the tank out, half a full tank out the top. It's just a different measurement or different bounds of integration. Okay, well, let's prepare on the next page for an additional problem, and we'll start it here in just a couple of minutes. Actually, less than that. Okay, our second problem. This time we have a spherical tank of radius 8 feet, and it's also half full of oil that weighs 50 pounds per cubic foot. Find the work required to pump the oil out the top in this case. So it's important that we start with a diagram, and we'll use a diagram quite a bit to get through this problem. It has its own little issues, a little different than what we had a while ago. So let me draw a diagram. Well, there's my three-dimensional sphere, and you can see, of course, that I've illustrated the level of oil in this spherical tank at 8 feet from the bottom of the tank. It's half full. The sphere is an 8-foot diameter sphere, radius sphere, so from top to bottom is 16 feet. Then the numbers are coincidental to what we had a while ago. So we're going to start out the same way. Remember, we're pumping it out a hole in the top here someplace, but we're going to start out as we did a while ago. We're going to first think about an infinitely thin slice of this oil that is in the tank, and in the part of the tank that has oil in it. So let's look here. Okay, we've got this little tiny slice of oil, and I apologize that this is kind of an ugly diagram. Okay, we're just thinking of a layer. Obviously, it's not solid there. And let's assume that that's at the y level. Okay, and of course, the y can be any value between 0 and 8 because the oil level is between 0 and 8 feet, or is 8 feet at the 8-foot level. So we can be in the oil as long as we're between 0 and 8 feet for y. As before, I'm going to call this width dy, or this height of that slice, basically. Now, and if you can imagine here, then, obviously, that is also that is a disk. What I've illustrated there is a disk, which is just a short right circular cylinder. So the volume of that slice, I'm going to abbreviate for S, once again is pi r squared times height. But here we have a different issue than we had before, because this is a sphere, the radius of that slice is not 8 feet. It's smaller than 8 feet. Remember, the radius being 8 feet is right across there. There's the 8 foot. Okay? So we don't have a radius of 8 feet when we're talking down here. Let me mark this in. There's the radius we're talking about, and that's smaller than 8 feet. If I had a better diagram, it'd be even easier to see. So the question is, what is this R value? See, that ends up being our question here, doesn't it? So, well, let's do this. This is where it comes in for us to recognize what we're doing. Now let's assume that this position is actually the center of the sphere. And notice I've drawn that horizontal line that is actually in the slice, in that little disc. Let's draw a vertical now, assuming that's in there, from the center of the sphere to the center of that slice. And then let's draw from the center of the sphere to the place on the edge of the sphere where the slice touches. Now, let me put that down here, okay? Let me just readjust that down here. It looks something like this, okay? Now, this value, let's remember, this is at the y level, and this is at the level 8, isn't it? And so this distance, I claim, that distance is 8 minus y. See, that's the height of that little triangle that I've drawn. And it's a right triangle that I've drawn. Okay, and you can see that's this distance right here, up here. That's the 8 minus y. Okay. Now, this is the R value that we're looking for. I didn't label it inside here, but that's the R value we're looking for up here for the volume of that slice. Now, the question is, what is the length of this hypotenuse? And I say the length of this hypotenuse is 8. And here's the reason I say that. In a sphere of radius 8, if we move from the distance from the center of the sphere to any location on the sphere is 8 feet in this case. And this point right out here, this point, which matches the point that we've got there, and if we look along the hypotenuse, this is the center of the hypotenuse, and we're going to a point on the sphere itself, well, that distance has to be 8. So we have a right triangle where one of the legs is 8 minus y units long, the other leg is r units long, and the hypotenuse itself is 8 units long. So what we end up with then is that 8 minus y squared plus r squared is equal to 8 squared. The square of the sum of the legs is equal to the square of the hypotenuse. So that allows me to solve for r squared. R squared is equal to 64 minus this 8 minus y squared. Now, why is that important? Because r squared, way back here at the top, is actually what I'm looking for, isn't it? That's actually what I'm looking for. Now, we can actually simplify this a little bit further, and by squaring 8 minus y there, we'd have r squared is equal to 64 minus, when we square 8 minus y, we'll get 64 minus 16y plus y squared. And then when we distribute, of course, that negative sign, we'll end up with 16y minus y squared. So back up here where we started, the volume of that slice is pi times r squared, and we calculated r squared to be 16y minus y squared, and the height of that slice is dy. So the force required to move that slice is the same as the weight of that slice, which is equal to the volume of the slice times the 50 pounds per cubic foot. And so we find out that the force is equal to 50 times pi times 16y minus y squared dy. And that's the force. Okay? Force. Okay, well, now we have a different issue because the work to move a slice, is the force times the distance that the slice is actually going to move. Now, we're taking this slice and we're moving it out the top of the tank. Well, so that means the work to move a slice is going to be the force, which is this real long expression that we've got up above. Okay, and let me say 50 pi times 16y minus y squared dy. The distance it's going to move, well, look where that slice is. Okay, that slice is at the y value. And so we've got to move that slice from the y value all the way out to the top at 16. And so the distance it's going to move is 16 minus y. It's moving 16 minus y. That's the distance that that slice is going to move. Well, as we clean this up to make it look a little better, remember this W is standing for work now. The work to lift that slice out the top is going to be 50 pi times 16y minus y squared times 16 minus y times dy. That's the work to move that one single slice. Now we could clean that up a little bit by actually multiplying out the 16y minus y squared times 16 minus y. And I have done that. And I got, when I did that, it simplified. I got 256y minus 32y squared plus y cubed. And of course, dy. Okay. So, bottom line now, the total work, see, that was just the work to move one slice. The total work, then we're going to calculate by adding up the work to move each infinitely small slice of that tank, that half-full tank out the top. And an infinitely small slice is this 50 pi, the work for an infinitely small slice. Let me write it this way because I'm trying to make a point. We're going to use the integral to add up the infinitely number of work elements because we have an infinite number of slices. Now, where are those slices going to start? They're going to start at the y value of 0, and they're going to stop at the y value of 8. That looks similar to what we did before. So the work then for the half-full tank to be moved out, pumped out, it's going to be the integral from 0 to 8 of 50 pi times 256y minus 32y squared plus y cubed dy. Now, of course, I would do a couple of things. And the first thing is I would factor out that 50 pi. And then my integral is going to be a little simpler looking. Maybe not simple, but simpler looking. And it's not difficult, it's just a little cumbersome. So as I integrate 256y, let's do this. As I integrate 256y, I would get 128y squared. And as I integrate 32y squared, I would get 32 over 3 y cubed. And then, of course, plus 1/4 y to the 4th. And that's going to be evaluated from 0 to 8. And when I did that, I got an approximate value. Okay, I rounded it to the nearest unit, the nearest integer, and I got 589,782 foot-pounds of work. Okay, foot-pounds of work. So it had its own twist. Now the next one we're going to do will also have a little twist, and we'll continue this on the next page. Okay, our third problem, and by the way, you'll notice in all of these I've made pumping out oil that has a density of 50 pounds per cubic foot. We could be pumping out fresh water, we could be pumping out salt water, we could be pumping out some other liquid that has a different density, a different weight per cubic foot, and we would just adapt appropriately. And in each of these cases, I've had a tank that's 16 feet tall, like I'm saying here, with a radius of 8 feet, and the tank's half full. Well, the tank could be 2/3 full, or it could be full to the 6 foot level, or, I mean, we would just adjust appropriately. I'm just making it, in this case, all similar, just so we can see compare the results, if you will. So, as I stated kind of after the fact, we've got an inverted cone tank, and the radius at the top of the tank is 8 feet. Of course, that's a different radius all up and down, obviously. But at the top of the tank, it's 8 feet. And once again, we're half full of oil, and the tank, that is the cone, the tank is 16 feet tall. So this would be, we'll say at the 0 level, and this would be at the 16-foot level, okay? And if we're half full of oil, this is at the 8-foot level. Now, we're going to do just as we've done before. We're going to take a slice of oil, okay? So we're taking a tiny slice here, and we're going to deal with what it takes to, the amount of work it takes to move that slice all the way to the top and out. So let's assume, again, that slice is at the y level, but of course the height of that slice is dy. Now, the volume of this dy slice, the volume of this dy, of the dy slice that we see over there. That's what we're working on. So volume of the slice, once again, is pi r squared times h. The problem here is, once again, with the r value, because the r value is not 8 at this level. The r value is something else. So let's kind of imagine, if you will. Here's what I'm going to do. We need to know what this y value, this radius is right there, okay? And that's the r value. So what I'm going to do is I'm going to imagine dropping a vertical here and noticing that this triangle I get, this is perplexing. That's the reason I'm showing this problem. Okay, look at this triangle. I can see the outline of this triangle. Okay, so this is at the top of the tank, and that's 8 feet. And what we have is a level here. This is our, okay, let's kind of go through this now. This is at the 0 level. This is at the 16-foot level. And this is at the level we're at, the y level, okay? And this is the radius that we're looking for. Okay, this is the radius that we're looking for. So what you see is that we actually have two triangles. We've got the big triangle, they're both right triangles, and we've got this littler triangle. And they're similar triangles because all three of their sides are parallel. So similar triangles, the ratio of sides is identical, isn't it? So what we could say here is that what am I getting at? We say let's consider the big triangle. So the ratio of the top side to the vertical side in the big triangle would be 8 to 16. Remember that top side is 8 and the triangle is 16 feet tall. So that ratio 8 to 16. So we're talking about this distance to this distance. Okay? And that's got to be, if we set up the same ratio in the smaller triangle, they've got to be equal. That's the idea of similar triangles. So in the smaller triangle, the side that is horizontal is this side, and that is r units long. Good, because we're trying to get a value for r. And the vertical side is this side of that triangle, and that's y units. Remember, that's what we were measuring as y a while ago. So this gives us this relationship that 1/2 is equal to r over y, or r is equal to 1/2 times y. Okay? And so now we have a relationship for r. Okay, now let's go back to our original work then. The volume of a slice is pi times r squared. And in this case, r is 1/2 y, so that's what we're squaring. And the height of our slice is dy. Now, obviously, we can make that look a little better by calculating that to be, let's see what that would be, 1/4 times pi times y squared times dy. So that's the volume of the slice. Okay? Well, the weight of that slice then would be its volume times the density of the oil. That is 1/4 pi y squared dy, and of course that's in cubic feet, times the density of the oil, which is 50 pounds per cubic foot. And so as we simplify that, we get, and I'm just going through the routine here, as we simplify that, we'll get 25 over 2 times pi y squared dy pounds. Well, remember, pounds in a lifting problem is the same as force. So when we're looking at the work required to move that slice out, it would be the force for that slice times the distance for that slice. And the force is overhead there. It's 25 over 2 pi y squared dy. Now the distance that's moving is from this level y, see, this is the distance that's moving. And that is, as before, 16 minus y. If we were moving all the way out, it'd be 16, but we're not moving all the way out because this is y units from the bottom. So 16 less the y that we're not having to move. So the distance in this case is 16 minus y, like we've kind of seen before. And so that ends up simplifying, if you will. We can make that look a little better by saying it's 20, well, there's a 25 up here, pardon me. 25 over 2 times pi, and of course y squared times 16 minus y would be 16y squared minus y cubed in our dy. So that's the work required to move one slice. Well, then from there, our total work would be adding up the infinite sum of the infinite number of work items. And we do that by integration. So as we've done before, we're going to add up the infinite number of work slices, if you will, to get the total work. But those work slices, we're starting the slices from a y value of 0 to a y value of 8. And so we set up this integral, the integral from 0 to 8, and our work slice is the 25 over 2 times pi times 16y squared minus y cubed dy. Now, I'm convinced that you could probably go from here. Let's factor out that 25 over 2 pi, and let's think about integrating the 16y squared minus y cubed, and we would get, what, 16 over 3 y cubed minus 1/4 y to the 4th, and we're evaluating that from 0 to 8. Now, we can do that, and I'm convinced that you can. It's a little tedious here, but not any big deal. And when we get that calculation done and round it to the nearest integer, we would have 62,021 foot-pounds. Once again, those are our units. So this had a little different twist. It's a little technique that you may have to use on your homework or some other problems in the future. As you can see, this problem is about lifting a chain. We have a 20-foot chain that weighs 5 pounds per foot, and it's lying coiled on the ground. The question is, how much work is required to raise one end of the chain to a height of 20 feet so that it's fully extended, as we see in the diagram. Now, I think the way to approach this problem is to incrementalize the parts of the chain, the length of the chain. So what I mean by that, so we're going to take this chain and we're going to break it into infinitely little pieces, okay? That's the idea, breaking it into infinitely little pieces. Well, one of those infinitely little pieces we'll see is a length of dy. Okay, so that's a length. There's an infinite number of those because they're infinitely small. So when we take one of those incremental pieces, the weight of one of those slices, kind of what I'm thinking, the weight of a piece of a slice will be 5 pounds per foot and a length dy given in feet. So that's the total weight for one of those infinitely small pieces. 5 pounds per foot, and remember dy is an infinitely small number of feet. So pounds per feet times infinitely small length in feet gives pounds. So that's the idea that this is in pounds. Okay? Now, the work of lifting a piece, well, work in general, again, of course, is force times distance. And in this case, of course, we're referring to the work required to lift one of this infinitely small slice or piece of chain. Well, the force required is its weight. And so that's the 5 dy. That's the force. Okay. Now the distance we need to think about a bit. So let's let this dy that we've got here represent the length of the chain, the infinitely small length of the chain that's being lifted, and it gets lifted to that position. Well, let's say that this position that it's at we'll refer to as y. Now sometimes that little piece gets lifted the whole 20 feet, Sometimes that little piece, depends on where it is in the chain, gets lifted 18 feet. There's a place on the chain where it gets lifted to 10 feet or 1 foot. Well, the place on this chain is being lifted to the Y foot level. That's where it's going, the Y foot level. So from the ground to that level, that distance is Y. That distance is Y. So our work of lifting that slice to the level that it will be 5y dy. Okay, well, the work to lift the entire chain, this is the total work, will be an integral. And it will be the integrate, will integrate, that is, we'll add up all of the pieces of work, if you will. But where's that work starting? Well, the entire length of the chain. We start at one end and go to the other, 0 to 20. It's going to be lifted from 0 to 20. Each piece of the chain, that is, as the chain is broken into those pieces. So the integral we get is the integral from 0 to 20 of the 5y dy. And that results in an integral that is, what? 5 halves times y squared, evaluated from 0 to 20. And that's clearly is 5 over 2 times 20 squared, minus 5 over 2 times 0. And when we do our work here, we end up with 1,000 foot-pounds. On the next page, we're going to do problem 5, which is the last problem, at least for now. Maybe later I'll add some additional problems. We'll pause as I write up the next problem on the next page. Okay, here you can see that the problem is about a demolition crane that has a 50-pound wrecking ball on the end of it, although it's not very large. And this ball is suspended from a 40-foot cable that weighs 2 pounds per foot. So I guess the question is this: how much work, find the work required to wind up 15 feet of the apparatus. Wind up 15 feet. Of the entire apparatus. So let's look at the problem this way. We don't really know that this ball is at ground level, but we know that the length of the cable suspending the ball from the end of the crane is 40 feet. So we're going to let that end where the ball is just represent our 0 level. And where the cable goes into the crane is at 40 feet, because that's the length of that cable at that point. So that we're going to kind of normalize things between 0 and 40. Now, after the crane winds up 15 feet, then we'll have the illustration over here, basically, in tow. And there's 3 different pieces to this problem that we're going to have to worry about. So let me describe those 3 pieces. There's kind of a total work is going to consist of 3 parts. And work 1, okay, I guess is the best thing to call it. So 1 is the work required to lift the ball. Okay. Well, the ball, the wrecking ball itself, It weighs what, 50 pounds? So I'm just thinking about the ball, how far is that ball being lifted? 15 feet. So the work to lift the ball is very simple. Work sub 1 is going to be the weight of the ball, the force represented by the weight, times the distance it's being lifted. So that's the weight, 50, and the distance it's being lifted is 15. 50 pounds, 15 feet, so that ends up being 750 foot-pounds. So that's very straightforward in terms of lifting that ball. Now, let's think about this part of the chain. So if you will, okay, let's look at this as the 25-foot level. Okay, 25-foot level, because the chain is, the cable, the whole thing is being brought in by 15 feet. So this part of the cable is going to be wound completely up, isn't it? From right here on, it's going to be wound completely up. So if you look at this bottom part of the cable, okay, so let's talk about the work 2 being the work required to lift the bottom 25 feet of cable. So we're thinking of the cable as one piece of work, the ball is another piece of work. So the work required to lift the bottom 25 feet of cable. Well, that bottom 25 feet of cable is all represented here. See, this is that bottom 25 feet now. Okay, that's the bottom 25 feet. After it's rolled up, that bottom 25 feet all got moved up 15 feet. So the bottom 25 feet was all moved up. It didn't go any further than that. It was all moved up the same distance, 15 feet. Well, so in this case, that work is going to be the weight of the cable. Okay, the force, it's the force, which is the weight, times the distance. Okay, well, in this case, there's 25 feet of cable, and it weighs 2 pounds per foot. So that cable itself, that 25 feet, is 50 pounds. Now, what was the distance it was lifted? Well, every part of that cable was lifted 15 feet. So this is in pounds, and this is here are pounds, and here are feet. So as we calculate that, what do we get? We'll also get 750 foot-pounds. Okay. Now, our third work, the third part that we're worried about, is the top 15 feet of cable. So now we're talking about this part of the cable. And that top 15 feet is getting reeled in or rolled up, however we want to say that, to wind up. Now, in this case, part of that cable is being, at the 25-foot level, is getting wound in 15 feet. But if we were at the 30-foot level, then that's only getting wound in 10 feet. So here we have a little more work to calculate, and pun not intended there. Okay, so this is the work required to wind in the top 15 15 feet of cable. So when we pick its position in this top 15 feet, then what do we got here? Okay, let me see if I can talk about that little slice. So we're now we have variable distances. That's the whole issue before, variable distances that we're moving, because parts of it move 15 feet, parts of it move just a few feet. So we need to know the force or the weight of what we're talking about, okay? So the weight of one of these incrementally small pieces, the weight of a slice of this cable, if you will, is going to be 2 pounds per feet, and we have got an infinitely small number of feet, so the weight is 2 dy. Now, and that acts as force also, remember, because we're lifting. So the work for one little slice in this top 15 feet of cable will be the force or the weight times the distance that it's going to move. Okay, well, let's stop and think about it this way. That y level is all of this distance. Okay, so the distance that part of the chain or the cable is going to move will be this distance up here, which is 40 minus y. So the distance it's going to move is 40 minus y. Remember, this is the force, and this is the distance. Well, we can make that look a little better by writing that as what? 80. Well, let's just leave it this way. Let's leave it as 2 times 40 minus y dy. Okay, so work 3 is going to be the integral from 25 to 40, because all of these y's, all these locations on that part of the cable start at the 25-foot level and go to the 40-foot level. And we're going to add up all the incremental pieces, as we've done here, the small work pieces, which was 2 times 40 minus y dy. So as we go through and calculate here, we would have an integral, and let me just fill in real quickly so that you can see what we would end up having, is we would end up having 2 times 40y minus 1/2 y squared evaluated from 25 to 40. And when we make that calculation, we'll get 225 foot-pounds. So the total work then will be work 1 plus work 2. Work 1, remember, was lifting the ball 15 feet. Work 2 was lifting the bottom 25 feet of cable 15 feet, plus work 3, sub 3. And what was that? 750 plus 750 plus 225, all in work in foot-pounds. And what is that? 1725, I believe. Yeah. 1,725 foot-pounds. Well, I hope these 5 problems have given you a jump start to the homework that you're going to be working on. I've tried to give several different examples, and I guess good luck now on the homework that is ahead of you. That's the end of this lecture.